Hello, welcome to my channel. Today we are diving into one of the most exciting revolutions in science, the rise of artificial intelligence. Over the past decade, AI has not only accelerated the pace of discovery, but has also refined how researchers approach problems, from decoding the human genomes to unraveling the mystery of the universe. In this video, we will explore how innovative algorithms and machine learning models are transforming traditional scientific methods, driving breakthroughs, and opening up entirely new field of inquiry. Whether you are a science enthusiast or just curious about how technology is shaping our future, stay tuned as we uncover the profound impact of AI on scientific research. Wait, hold on. If you haven't already noticed, I requested AI to compose the introduction of this video. Let's rewind and find out.
Welcome to my channel. Today we are diving into one of the most exciting revolutions in science, the rise of artificial intelligence. Over the past decade, AI has not only accelerated the pace of discovery, but has also refined how researchers approach problems, from decoding the human genomes to unraveling the mystery of the universe. In this video, we will explore how innovative algorithms and machine learning models are transforming traditional scientific methods, driving breakthroughs, and opening up entirely new field of inquiry. Whether you are a science enthusiast or just curious about how technology is shaping our future, stay tuned as we uncover the profound impact of AI on scientific research.
As we enter a new era, AI is indeed evolving beyond mere automation to become a powerful partner in the pursuit of knowledge, from accelerating drug discovery to uncovering hidden patterns in the vast dataset. AI is redefining the way we conduct scientific research. Furthermore, the 2024 Nobel Prize in Chemistry has been awarded to scientists who pioneered the novel methodology of employing AI to elucidate protein structures. Given that AI-related stocks have reached record highs, AI scientists have gathered the most prestigious scientific awards, and the ensuing concerns among the general public regarding the future of their occupations and livelihoods. This makes me wonder, can we rely on AI to perform scientific research? To provide the best science content to my audience, I regularly acquire new chemicals and apparatus for my scientific projects. Recently, I inadvertently received an incorrect bottle of chemical during a purchase. The seller was generous enough to ask me to keep it. Consequently, now I possess a bottle of D-Mannitol, which I know limited knowledge about. While I do hold an advanced degree in chemistry and materials science, I'm not specialized in carbohydrate chemistry or the related biochemistry. In general, I can tell from its molecular structure that it's a sugar alcohol, which means it's reduced from a sugar, and it is mostly utilized as an artificial sweetener. But beyond this, my knowledge of the potential experiments that a home chemist can do with it is limited. So naturally, I turned to AI for help, and this is a list of experiments that AI suggested. The first one, Mannitol crystal growth experiment. Mannitol melting and solidification. Freezing point depression. Plasmolysis in plant cells. Mannitol and iodine complexation. Mannitol as a reducing agent. Mannitol foam formation. Mannitol as an artificial sweetener experiment. Among them, I have chosen several experiments that can be performed here. So let's find out whether these experiments can be successfully executed as suggested by AI. First, let's choose from the list what experiment we would like to do. The first three items, crystal growth, melting, and freezing point depression, are not something that's unique to mannitol. Plasmolysis sounds interesting, but since I'm not a professionally trained biologist, I'll skip this one too. The next two items, iodine complexation and the reaction with metal ions as a reducing agent, have gained my attention. These properties, if they were true, could be unique to the physical and chemical properties of mannitol, and they would have provided fantastic visual effects for our videos as well. In regards to foam formation, I guess your hand soap would probably work better. Lastly, since the mannitol I acquire is for lab use, despite its being analytically pure, we should never taste anything that comes out from our home lab. Without further ado, let's explore experiments 5 and 6. Experiment 5, according to AI, uses mannitol to react with elemental iodine, anticipating a color change. As far as I know, this property is unique to the iodine-starch interaction, which gives rise to a deep blue color. It would be extremely interesting if mannitol could form a color complex with iodine as well. First, I made a mannitol solution and stirred it until it's clear. Then, to test my pharmacy-grade iodine tincture, I have prepared two solutions. The cup on the right contains starch solution, and to the cup on the left, I carefully added some sodium thiosulfate solution. This is my iodine tincture. I poured some to a beaker and carefully added the iodine tincture solution to the two cups. Upon contact with sodium thiosulfate solution, the iodine lost its color immediately and was reduced to the colorless iodide ion. When added to the starch solution, iodine forms a deep blue complex with starch. This observation confirms that my iodine tincture indeed contains a reasonable amount of elemental iodine that can be used for the subsequent test. We can then proceed to perform the AI-suggested experiment. First, I added the mannitol solution that was prepared a moment ago. Then, I carefully added the iodine tincture solution. It appears that nothing had happened. You may ask why I'm using cups instead of beakers for this experiment. Elemental iodine is renowned for its tendency to discolor its surroundings, so I'm using cups rather than beakers for this experiment. After a period of time, I gently shook the solution. Although the color appeared to be slightly more uniform upon mixing, no color change was observed. It still looks like the original color of the iodine tincture, which suggests free elemental iodine is still present, and hence no chemical reaction occurred. To prove this, I had again prepared the thiosulfate solution on the left and the starch solution on the right. This time, instead of adding the iodine tincture, I carefully added the pre-prepared iodine mannitol solution to the two cups. We can observe that the cup on the left quickly turns colorless, and the cup on the right had generated a blue color complex. That being said, the AI had wrongfully predicted the reaction between mannitol and elemental iodine, as they do not form a colored complex with each other. Before moving on to the next experiment, it is imperative to properly dispose of the waste generated from the current one. The waste disposal procedure is quite straightforward. Simply add any solution containing iodine to an excess of sodium thiosulfate solution. Upon the solution becoming clear and colorless, it is safe to pour it down the drain with a large volume of water. Now that we had proven the invalidity of experiment 5, let's now take a look at experimental 6. Here are the instructions provided by AI. First, I added the pre-made mannitol solution into a beaker. Next, I prepared a solution of copper sulfate, which has a characteristic blue color. Then, I added several milliliters of the copper sulfate solution into the mannitol solution. However, no immediate reaction was observed. Here I have added more copper sulfate solution. After a while, still no change occurred. Now you are watching the video at 4 times the normal speed. Since nothing appears to be happening, I will play the time-lapse video for the next part. Considering the instructions provided by AI mentioned warming up the solution, I've prepared a hot water bath and the water was boiling just a moment ago. Despite this, nothing happened for the next 30 minutes or so. In fact, no obvious reaction occurred for the entire course of this reaction. If you recall your high school chemistry and biology classes, reducing sugar can be detected by Filling's solution and the Benedict's solution, whose active ingredient is some form of copper-2 ion. The reason is that reducing sugar generally contains an aldehyde group, which can reduce the blue copper-2 ion into copper-1 oxide, which is a brick red color precipitate. However, if you examine the structure of mannitol, no aldehyde group was present. Instead, it's considered a polyol due to the multiple hydroxyl group present in its structure. Unlike their aldehyde counterparts, polyols in general cannot reduce copper-2 to copper-1. Nonetheless, the corresponding sugar of mannitol, mannose, does contain a free aldehyde group. If mannose was used in this reaction, we would anticipate a color change in the reaction mixture. Therefore, it's safe to conclude that no obvious reaction can be formed between mannitol and copper sulfate, and the AI also made an incorrect prediction for experiment 6. So far, we had explored the 2 AI-composed experiments regarding D-Mannitol, and both of them were wrongfully made up by AI. While AI has emerged as an extremely powerful tool, it still has a long way to go before it can fully comprehend the underlying concepts and logics of scientific study. Let's end our video on a high note. We can't just end it with a failed experiment. So what experiment can we do with mannitol? Mannitol has multiple hydroxyl groups in its structure, which means it has moieties of primary and secondary alcohols. Both of them can be oxidized by potassium permanganate solution. So I thought, why not do the famous chemical chameleon demonstration with the D-Mannitol instead? So I had prepared a basic potassium permanganate solution by adding sodium hydroxide and the potassium permanganate solution sequentially, as you saw on the screen. Then I added some mannitol solution prepared earlier. If our prediction was correct, the solution would then display a wide variety of colors. Considering hydroxyl groups are generally less reactive than an aldehyde group, it would take a little longer to fully display the full range of color change during the course of the reaction, compared to the more commonly seen demonstration that uses a reducing sugar. This turns out to be a great thing since it allows us to take our time to appreciate all the colors it produces. I'll play some relaxing music in the background, and you can count how many colors did you see through the entire course of this reaction. That concludes the video for today. Hope you had learned something new. It takes a lot of time and effort to make a video like this. If you are intrigued by this video, please feel free to like, subscribe, share, and comment so I can create more videos like this. See you next time!